Welcome back, everyone. You're tuning into The Explainer. Today, we're doing a rapid-fire, one-shot review of the absolute bedrock of computer science, data structures. Specifically, we're demystifying arrays and linked lists. So let's jump right in and build that rock-solid foundation.
Here is our roadmap. We're looking at what a data structure actually is, comparing linear versus nonlinear, diving into arrays, comparing arrays to linked lists, and finally, breaking down singly and doubly linked lists.
Section 1. What is a data structure? We're going to use the refrigerator analogy to really ground this concept before we get bogged down in any code.
Okay, so what do mom scolding and data structures have in common? Imagine walking into your kitchen, opening up the fridge, and just shoving a ketchup bottle right into the crisper drawer with the veggies, or, leaving a tub of ice cream on the bottom shelf. You're absolutely getting scolded for that. And why? Well, because you didn't follow the system. Everything has its proper place.
And that perfectly illustrates our core concept. Just like a well-organized fridge, a data structure's main job is to store items based on their attributes. Ice cream goes in the freezer, right? Veggies go in the crisper. When things are organized like this, you can access them easily without digging around forever. You just open the door, grab the ice cream, and go. And finally, it lets you manipulate items efficiently, like putting water in the freezer to make ice. In the digital world, it's the exact same thing, just with data instead of groceries.
Section 2. Linear versus nonlinear. Now that we've got the basics, let's look at the two broad categories these structures fall into.
Think of linear data structures as arranging items adjacently, one right after the other. It's a single run from start to finish. Honestly, it's a bit like passing a nursery exam. Super straightforward, single level, one and done. Nonlinear structures, those are a whole different beast. They have multi-level hierarchies with complex relationships. Surviving a nonlinear structure is way more like surviving an engineering placement exam. You've got the aptitude test, the group discussion, the technical interviews. It's intense. But don't worry, for today's explainer, we are strictly sticking to linear.
Section 3. Arrays in the classroom benches. Time to dive into our very first linear data structure.
A classroom actually models an array perfectly. Technically, an array is a linear data structure that stores elements in contiguous memory locations. But just picture 10 students sitting on continuous classroom benches. No gaps, just sitting right side by side. If a teacher wants to call on a specific student without yelling, "Hey, you in the back," they use roll numbers. And in array, those roll numbers are called indices. And because the memory is continuous, if you want the data at index 5, boom, you access it instantly. It's lightning fast.
But arrays definitely aren't perfect, especially if you're searching for something and you don't actually know its index. Imagine going to a party on the 100th floor of a building. You walk all the way down to the lobby, only to realize you lost your expensive watch. So what do? You literally have to start at the first floor and traverse upward, floor by grueling floor, until you finally find it on the 100th floor. This is exactly the worst-case search scenario in an array. Because you didn't know the exact index, you had to scan sequentially from the very beginning. If your data is hiding at the very end, or worse, isn't there at all, it takes a massive amount of time. And that brings us to the ultimate villain of arrays, insertion and deletion. Picture standing in a huge line at the movies. You spot your friend way back in the queue and wave them up to cut in right in front of you. What happens? Literally everyone behind you has to physically shuffle backward one spot just to make room. That's how an array works. Inserting or deleting an element in the middle means you have to shift all the subsequent elements in memory. It's a massive mechanical headache and honestly, highly inefficient.
Section 4. Array versus linked list. The fierce battle. So if arrays give us these shifting headaches, what's the alternative? Let's treat this like an epic boxing match.
Let's look at the tail of the tape here. Arrays use contiguous adjacent memory. Linked lists, non-contiguous. Their elements can be scattered all over the place. Because arrays are contiguous, they win massively on access speed. You get that fast random access via indices. Linked lists, on the other hand, force you to search sequentially. But wait, linked lists hit back hard when it comes to insertion and deletion. Because they aren't contiguous, inserting is super fast. No shifting required, just a quick pointer swap. And finally, arrays are static and fixed in size, which can waste memory. Linked lists are totally dynamic. They grow and shrink exactly as you need them to. Moving on to Section 5, the singly linked list. Let's break those chains of fixed memory and look at our flexible challenger. The crucial thing here is understanding the anatomy of a node. Since a linked list's data isn't just sitting side by side on a continuous bench, How on earth do they connect? Well, each node has two parts. First, the data field. That stores your actual value, like the number 10. Then there's the link field. This stores the exact memory address of the next node in the chain. It's literally like a treasure hunt clue pointing you to the next location. We also have a head pointer, which just tells us where the whole list begins. And at the very end of the chain, that last link field just points to null, which is basically a stop sign, signaling the list is over.
Now remember how annoying it was to insert your friend into that movie theater line with an array? Check out how beautifully a singly linked list handles inserting a brand new node right at the beginning. Step 1, you just create a new node with your data in some random, free spot in memory. Step 2, you take that new node's link field and point it to whatever the head pointer is currently looking at. Step 3, update the head pointer so it points to your new node. Boom, you're done. No shifting, no sliding, no rearranging hundreds of elements, just a couple of invisible pointer changes.
And deletion is just as elegant. If you want to delete a node right in the middle of the chain, you don't have to close any gaps by shifting everything over. Step 1, identify the node you want to axe. Step 2, take the node right before it and change its link field to just bypass the deleted node entirely, pointing straight to the node after it. Step 3, free up the memory of that now isolated node. It's an incredibly clean link bypass that securely removes a node from the chain without disturbing anything else.
Section 6. Doubly linked list. The two-way street. Because what happens if you're traversing your list, searching for something, and you accidentally go right past it? In a singly linked list, you literally have to start all over from the head. So let's look at the ultimate evolutionary upgrade.
I absolutely love this quote. One-way streets are hard for U-turns. Doubly linked lists give you a two-way street. It's so true. Singly linked lists only let you move forward. If you miss your stop, well, you're out of luck. But by adding just one more pointer to our node architecture, we unlock total navigational flexibility.
Let's look at how the structural upgrade actually works. A doubly linked list node has three distinct parts. Right in the middle, you still have the data field. That's your core info. Over on the right, you have the next pointer connecting forwards, just like we saw before. But on the left, now you have a previous pointer. This connects backward to the node right behind it. And because we can now move in both directions, we get dual nulls. One caps the extreme start of the list, and the other caps the extreme end. Now, since we have two connections per node, wiring a new node into the middle of a dual-linked chain takes a little bit more care, but the logic is still pretty brilliant. First, find your target insertion spot. Second, take your new node and set its next pointer to the node ahead of it and its prev pointer to the node behind it. Finally, you just update those surrounding nodes. The one behind points its next pointer to the new node, and the one ahead points its prev pointer to the new node. It's like they're embracing the new arrival from both sides. It is a few more steps, sure, but the two-way flexibility this gives your program is absolutely massive.
And that brings us to the conclusion. It's your turn to code. We've gone on quite the evolutionary journey today, from defining what data structures even are, all the way through the rigid speed of arrays and into the dynamic flexibility of linked lists.
So, what's the big takeaway here? Well, neither structure is objectively better than the other. Arrays offer a simple, continuous structure with crazy fast access times, if you know your index, but they're super rigid and absolutely hate shifting. Linked lists offer dynamic freedom, effortless insertions, and zero wasted memory, but you're stuck traversing them step by step. They each have distinct strengths tailored for very different scenarios. You really have to choose your weapon wisely based on what your specific application needs to do the most. I'm going to leave you with this thought. Think about an app you use every single day, or maybe even one you want to build yourself. Does it need lightning-fast lookups of a fixed number of items, or is it constantly adding and deleting real-time data on the fly? Which data structure would you choose to build the foundation of your own custom app? Think about it, and more importantly, open up your editor and start experimenting. Thanks for joining me for this explainer, and keep learning.